In today's review, I will start from the function limits or the limits of a sequence of functions. So first, I will give the definition of function limit. Limits of a sequence of functions. Let Fn be a real value function defined on E. Then we say Fn converges pointwisely to F if for every point in E, the limit of Fnx is Fx. So in this case, we write Fn converges to F simply by this. Also, let's first give some examples. If Fnx equals x over n, then Fn are raised from the 0 point. So this is F1, and this is F2, and F3. So it will turn to 0 as n tends to infinity. That is for every fixed point x. As n tends to infinity, this will tend to 0. So Fn will converges to 0 function pointwise. For the second one is the Fnx equals xn. Oh, here x is on the real line. X is in the interval, closed interval 0 and 1. Then Fn will be curves connecting 0 and 1. F1, F2, F3, F4. So it will close and get closer and closer to the real line. But there's something different to this case is that F will equals to 0 if x is in 0 and 1 except at the end point, because one n is equal to 1. So it will converges to some function like this. Okay, next one. Fnx equals sine x over n, where x is the real number. So graph is like this. This is F1. and f2 f3. So it will convert toward 0 because sine x is bounded by 1. So these are the limits of a sequence of a function. Next, we define the norm of f. If f is bounded, then we define the norm of f to be the supplement of f. So the norm of f means that the maximum difference from f to the 0 function. So in this case, the norm of f1 is 1, and norm of f2 is 1 over 2. It's like this. So after we have this such notation, we can define a stronger convergence. We say Fn converges to F, converges uniformly to F if for all epsilon larger than 0, there exists n larger than 0 such that for every n larger than n, the distance between Fn and F is smaller than epsilon. So why we want to define the norm like this is because it gives us the distance. We can define distance in the function space. So for example, this is the distance between f and the 0 function. And this says that if Fn, the maximum difference between Fn and F is more than epsilon, then we say their distance is more than epsilon. Okay, we calculate some example here. In this case, F is not bounded, so we don't consider this function. What about this? Does Fn converge uniformly or not? We have the norm sine x and minus 0 is more than 1 over n, because sine x is bounded by 1. So there is this n such that epsilon is larger than 1 over n. So this condition is satisfied. So Fn converges uniformly to 0. But what about this? Distance between xn and 0 is more than epsilon if and only if x is more than epsilon 1 over n. smaller than 1 when epsilon is smaller enough. So this means that we can find y larger than 0 such that y is between epsilon 1 over n and 1, which implies y n minus 0 is larger than epsilon. So when n are fixed, when epsilon is fixed, we can find for every large enough n, we can find y that is very close enough to 1. So the distance between f and y and 0 is larger than epsilon. So we cannot find an n that bound the distance. So Fn does not converges uniformly to F. Next, we define our functions, our function space. The function space CBE is equal to the function real value function defined on E such that f is bounded and continuous. Then CBE is a metric space with metric DFG equals the norm of F minus G. So this is our metric space of functions, and we define the distance of functions as the maximum difference between them. So why we are considering uniform convergence? Oh wait, you can see that in this definition is exactly the definition of limits of a sequence. But now the points are functions. And this is the distance between functions. So why we are consider the convergence of a uniform convergence instead of point-wise convergence? It's because in this example, if we consider only functions that converge point-wise, then xn is continuous on the interval 0 and 1. But it will in the end, it will converge to some function that is not continuous, like this. So the limit point is not in our metric space. So we don't want such thing happen. So we need a stronger convergence. So if we will show that if Fn converges uniformly to F, then F will be continuous. So the limit of Fn will in the matrix in our metric space. So our metric space will be complete. Is that okay? So we prove that if Fn converges uniformly to F, and F is bounded and continuous, then at Fn, then it will converge to the function that is bounded and continuous. Proof. Okay, to prove F is continuous, we compute Fx minus Fy when x and y is close enough. It will bounded by Fx minus Fnx plus Fnx minus Fny plus Fny minus Fy. So in this term, as n tends to infinity, because u is uniformly converges to f, we can find n large enough such that this two term will smaller than some epsilon. There exists n largest enough Fnx minus Fx is more than epsilon. It's more than epsilon over 3. What about this part? This part is same as this part. What about this? This can be bounded. This is bounded by epsilon because Fn is continuous. So for every epsilon larger than 0, we can choose delta larger than 0 such that Fnx minus Fny is more than epsilon over 3 when x minus y is more than delta from the definition of continuity. So Fx minus Fy is more than epsilon over 3 plus epsilon over 3 plus epsilon over 3, which is epsilon. So F is continuous. So the delta we take in here is the same as here. Okay. The left is to prove F is bounded, which is F is open. Because this is because Fx is more than Fnx minus Fx plus plus Fnx. So this implies the norm of F is smaller than minus F plus F. and this is bounded by epsilon, some epsilon, and this is bounded by some constant m. So f is bounded. Oh, notice that you have to check that this matrix, this function space with the metric here is indeed a metric space. You can check it very easily by definition.
Wait, so that's a U, not an N.
Oh, yes, that means uniformly. Next, we show that the uniform convergence of Fn is equivalent to the Cauchy sequence in the function space. So if Fn converges uniform to F, then such sequence is a Cauchy sequence in the function space. And only if Fn is Cauchy in function space. So what if we have this? After we have this, because the convergence sequence is Cauchy. No. For every Cauchy sequence in the function space, we know that it converges uniformly to some f, and by this theorem, f is bounded and continuous. So the point or the function it converges to is in the space CBE. So this space will be complete. Okay, we first prove this way. So to prove Fn is Cauchy, Fn minus Fn is smaller than Fn, the distance between F and F plus the distance between Fn and F by triangle inequality. And by uniform convergence, we can choose n large enough such that this term and this term is more than epsilon 2 over 2 plus epsilon over 2 equals epsilon. By choosing n larger than n. The converse part is a little bit harder. We first consider any fixed point in E. Then Fnx minus Fnx is more than epsilon for every Nm that is larger than n. So Fnx is a Cauchy sequence in R. And since R is a complete space, it must converge some points. So since R is complete, Fnx will converge towards some point Fx in R. So for each point in E, we can find the convergence point of Fnx. So with that, the convergent point in E to be the function of f. So Fn will converge to some f pointwisely. So next we need to show that this convergence is actually uniform. So since Fn converges to f pointwisely, so for every point in E, we can find some n depend on x that is larger than n, such that the distance between Fmx and the Fs is more than epsilon. So the distance between Fx and Fnx is smaller than Fx minus Fnx plus Fnx minus Fnx. So this part is more than epsilon, and this part is more than epsilon by the condition, by the Cauchy condition. For all n of less than n. So taking epsilon equals epsilon over 2, we are done.
Yeah, one thing I do want to point out that I'm not sure if you understand the statement that Fn, this sequence of function, is Cauchy, but in this function space. Because usually when we think of Cauchy, it's a sequence of numbers in the like R or Rn or something. But yeah, that is something that I think is not trivial. So the CNE is a
CBE.
Oh, CBE.
Means folded.
Yeah, okay. CBE is so it's a metric space of functions. That's why it's
That is a little bit.
So it's a metric space of functions, not of because we usually see metric space of points or in Rn. So that's something that's you have to get used to. But that is the dark magic of mathematics, where you can turn functions. You can have a structure of structures.
Yes. So as we say before, the corollary is CBE is complete by the previous two theorems. So that's why we consider functions bounded and continuous. So this is a strong property, but how can we use this one? There is a famous property can be proved using the theorem. That is, there exists a continuous function on R that is nowhere differentiable. So in the last course, we say that a continuous function is not necessarily differentiable because it may have some points that is not differentiable, or even 2 or 3. But in fact, a continuous function can be really, really bad, so you can't find any points on it that is differentiable. But it is difficult for us to write such function, to construct such function directly. So what we do is we use a sequence of function that will have more and more points that is not differentiable, and and in the end it will converge toward a function that is nowhere differentiable. I think I will draw like a diagram. So first we consider our first function like this. So with infinitely many triangles on the real line. So this function will have infinite point that is not differentiable, and here. And next we double the point that can not be differentiable. That is this. That is F2. So our F3 will be double again, something like this. So we can then we can summing this function up. So F1 will be this, and F1 plus F2 will be something like this, and F1 plus F2 plus F3 will be something like this. So as n becomes larger and larger, it becomes steeper and steeper everywhere. So in the end, it becomes nowhere differentiable.
There's a joke about this function, like, interval 区间测数. So the principle of like 区间测数is like to take note on your time when you pass a recording point. So that if, let's say, it's like, let's say 70, but and you pass it in an hour, but there's a maximum speed of like 60 km/h. So that you're speeding in this interval. Right, that's the principle. But why this work? It's because mean value 0. So that because I know you're driving through this in this time and this distance, so that you must like speeding at some point. So it's like the police obviously say, okay, I see you're speeding because like, this kind of 区间测数 system. You can say that my trace function is but nowhere differentiable, so you cannot apply min max theorem on that. So I'm not speaking. That's like nerd joke.
Are you sure the police understand?
I'm not so
No,
sure.
but the police can define the average velocity and the trouble is gone. Because you don't actually.
But you actually, you're saying that your speeding is the
And so the law can be. not-
yeah, the low can be the average.
Okay, I will give this is an example in routing. Given in routing, I will give a construction, but I will not prove it. If you are interested in how to show this function is not differentiable everywhere, you can see I think in chapter 9 or 7, I forgot. Okay, so our function is absolute function when x is between 1 and -1. Then we extend the function by x plus 2 equals x. So we can extend our absolute function infinitely. Then with that f equals the sum of 3/4 n times 5 for n times x. Then f is continuous but nowhere differentiable. Note that we are adding these 3/4 terms because we want our sum to converge. Otherwise, something will happen that it equals 1 minus 1, 1 minus 1 plus 1 plus 1, something like this. So this term ensure our function will be bounded. And you can check that this function, if this we erase this to be n, this function will convert uniformly to f. So fx will be continuous by our previous theorem. So the next thing you need to prove is such function is not differentiable by checking directly the differentiability at some point, which is a little bit tricky. Okay. That's the end of the review. Any questions?
So will this be in the next quiz?
You say this function?
No, the whole lecture.
The whole lecture, this will not in the quiz. Okay? And the sequence of function is important because this is a preview and this is what you will learn this week. I think